Graphical representation of functions. So far we've been discussing functions, what they are, how they map inputs to outputs. Now, we're going to move on to how we can see those functions, how we can visually represent them. This slide introduces the idea of graphical representation of functions. Essentially, we're going to learn how to draw a picture that shows what a function does. Specifically, in this section, we'll be looking at functions that are defined using sets, remember? A set is just a collection of things. We'll be taking those set definitions and turning them into graphs. And don't worry if this seems a little abstract right now. We're going to build up our understanding step by step, starting with some really simple examples. We'll go through the process carefully so you can see exactly how it works. This will lay the foundation for understanding graphs of more complex functions later on. In the following slides, we'll break down the connection between these sets and the graphs they create, and then walk through the steps to create those graphs yourself. Understanding the connection between sets and graphs. Now recall that a function, and I'm writing this as f, a maps to b, simply means that for every element in set A, which we call the domain, the function assigns exactly one element in set B, which we call the codomain. Think of it like a machine. You put something from A into the machine, and it spits out something from B. It always spits out something, and it's always just one thing. To visually represent this relationship, we use what you're already familiar with, a coordinate plane. You know, the one with the horizontal and vertical axes. Now here's how we connect the sets to the plane. We typically plot the elements of the domain, that set A on the x-axis, the horizontal axis. So each value in A will have a position along that axis. Then the corresponding elements from the codomain, that set B, the outputs of the function, we plot those on the y-axis, the vertical axis. So, for each input on the x-axis, there's a specific output value on the y-axis. And here's the key. Each mapping from the function, each input-output pair, becomes a point on the graph. If x is an element in A and f of x is its corresponding element in B, we plot the point with coordinates x, f of x. We'll see this in action with some examples coming up, but essentially, the graph is just a collection of these points, visually showing how the function transforms inputs into outputs. This is the foundation of understanding functions graphically. So let's move on to slide 2. This slide is really about connecting what we know about functions, those sets and mappings we talked about on the previous slide, to how we see them on a graph. Steps to graph a function defined by sets. So now that we've discussed how functions connect sets and how that can be visualized, let's break down the exact steps to actually graph a function that's defined using sets. This is slide 3, and it's really the how-to guide for everything we've been building towards. Step 1, identify the domain and codomain. This is fundamental. Remember from our earlier discussion, the domain, we call it set A, is all the possible inputs to our function. The codomain, set B, contains all the possible outputs. So before you even think about drawing anything, you need to clearly write down what those two sets are. Knowing these sets is the foundation for setting up our graph correctly. Step 2, determine the function's mapping. This is where we understand what the function does. How does it take an input from set A and transform it into an output in set B? This mapping is often given to us as a set of ordered pairs. For example, we might be told that f of 1 equals 2, f of 2 equals 4, and so on. Understanding this relationship is crucial because each of these pairings will become a point on our graph. Step 3, create a coordinate plane. Now we get to the visual part. Draw your standard x and y axes. The x-axis will represent our domain, set A, think of it as the input axis. The y-axis will represent our codomain, set B, the output axis. Now, this is important. Scale your axes appropriately. Make sure the numbers on your axes can accommodate all the values in both set A and set B if your domain goes from -5 to 5. Your x-axis needs to cover that range. Step 4, plot the points. This is where the mapping from step 2 comes into play. For each element, let's call it x. In our domain A, we find its corresponding output, which is f of x. In the codomain B then, we plot the point with coordinates x, f of x on our coordinate plane. So if f of 1 is 2, we plot the point 1, 2. We repeat this for every element in the domain. Step 5. Analyze the graph. Once you've plotted all the points, take a step back and look at them. Do they form a straight line? A curve? Are they scattered randomly? The pattern, or lack thereof, in these points tells us a lot about the function's behavior. This visual representation can often reveal things that aren't immediately obvious from just looking at the set definition. Now, in the next slide, we'll walk through a concrete example to really solidify these steps. We'll see how this all works with a specific function and its corresponding graph. So, make sure you understand these 5 steps before we move on. Example 1, a simple function. Let's move on to our first example of graphing a function defined by sets. As we discussed in the previous slides, understanding the connection between sets and graphs is crucial. Now, we'll put that understanding into practice. Here, we're considering a function, which we'll call f, that maps from a set A to a set B. Remember, this is written mathematically as f, a maps to B. In this specific case, set A contains the elements 1, 2, and 3, and set B contains the elements 2, 4, and 6. The function itself is defined by the equation f of x equals 2 times x. This simply means that whatever value you input for x, you multiply it by 2 to get the output. Let's break down the steps. First, we clearly identify our domain and codomain, which we've already done. A is the set containing 1, 2, and 3, and B is the set containing 2, 4, and 6. Next, we need to determine the function's mapping. This means finding out what f does to each element in set A. So let's calculate. F of 1 is equal to 2 times 1, which equals 2. F of 2 is equal to 2 times 2, which equals 4. And finally, f of 3 is equal to 2 times 3, which equals 6. Now let's create our coordinate plane. Remember, the horizontal axis is the x-axis, and the vertical axis is the y-axis. We'll use the x-axis to represent our domain, set A, and the y-axis to represent our codomain, set B. We need to scale our axes appropriately. On the x-axis, we'll mark the values 1, 2, and 3. On the y-axis, we'll mark the values 2, 4, and 6. Now comes the plotting part. For each element in our domain, we'll plot the corresponding output as a point on the coordinate plane. So, for x equals 1, f of x is 2, giving us the point 1, 2. For x equals 2, f of x is 4, giving us the point 2, 4. And for x equals 3, f of x is 6, giving us the point 3, 6. Finally, let's analyze the graph. If you look closely, you'll notice that the 3 points we've plotted lie on a straight line. This is a very important observation. It tells us that there's a linear relationship between the input and the output of this function. In other words, as x increases, y increases at a constant rate. This example demonstrates how we can visually represent a function defined by sets using a graph. Keep this in mind as we move on to the next example, where we'll explore a function with a slightly different domain. Example 2, a function with a limited domain. Let's move on to our second example. As you recall from the previous slides, we've been looking at how to represent functions graphically using sets. Now, this example is a little different from the first one, where our domain consisted of numbers. Here we're considering a function, f, that maps from a set A to a set B. Set A contains the elements B and C, and set B contains the numbers 10, 20, 30, and 40. So, f takes elements from the set A and maps them to elements in set B. Let's break down the steps. First, we identify the domain and codomain, which we've already done. A is the set containing a B and C, and B is the set containing 10, 20, 30, and 40. Next, we determine the function's mapping. In this case, it's already given to us. The function f maps A to 10, B to 30, and C to 20. Now let's create our coordinate plane. Remember, the x-axis represents our domain, set A, and the y-axis represents our codomain, set B. Instead of numbers on the x-axis, we'll mark the letters B and C. On the y-axis, we'll mark the numbers 10, 20, 30, and 40. It's important to space these out appropriately so we can accurately plot our points. Now for the plotting, we take each element from the domain and its corresponding output. So for A, the output is 10, giving us the point 10. For B, the output is 30, giving us the point B 30. And for C, the output is 20, giving us the point C 20. Finally, let's analyze the graph. Notice something different about this graph compared to the first example. The points do not form a continuous line. Why is that? It's because our domain consists of discrete elements, A, B, and C. These aren't consecutive numbers like 1, 2, and 3. We only have defined values for the function at these specific points. This is a key distinction. If your domain is a discrete set, you won't have a continuous line or curve, you'll just have individual points. Remember this as we move forward, because in the next slide, we'll discuss some common mistakes to avoid when graphing functions. Common mistakes. Now, remember from the previous slides, we talked about setting up our coordinate plane, the x and y axes. Incorrect scaling happens when you don't choose a good range for the numbers on those axes. If your domain or codomain has large or small values, you need to make sure your axes are scaled appropriately to show all those values clearly. If you squeeze everything in too tightly or leave too much empty space, your graph won't be accurate. So, always double-check that your axes cover the entire range of values present in both your domain and codomain. This is a really common one. When you're plotting points, it's easy to accidentally swap the x and y values. Remember, the x-coordinate always represents the input. That's a value coming from your domain, the set A we discussed earlier. The y-coordinate represents the output, the value you get after applying the function, which comes from the codomain, set B. So, always think, input on the x-axis, output on the y-axis. This one builds on what we saw in example 2. If your domain consists of discrete elements, like letters or specific numbers, not a continuous range, don't automatically assume that the points you plot will form a smooth line or curve. In example 2, we had the domain as a B and C. These are separate, distinct points. Connecting them with a line wouldn't make sense because the function isn't defined for values between a B and C. Let's move on to slide 6, where we discuss some common mistakes students often make when graphing functions. It's good to be aware of these before you get stuck, so we can avoid them. Keep these 3 points in mind as you practice graphing, and you'll be well on your way to mastering this skill. Now, let's move on to the final slide where we'll summarize the key takeaways from this section. Key takeaways. Graphical representation provides a visual understanding of functions. Essentially, what we've been doing with these examples, taking functions defined by sets and plotting them, allows us to see how the function behaves. It's much easier to grasp the relationship between inputs and outputs when you can visualize it. Remember back to our definition of a function. It takes something in, does something to it, and gives something out. The graph is just a picture of that process. Each element in the domain maps to a unique point on the graph. This is a fundamental concept. Remember the domain? That's the set of all possible inputs for our function. Each of those inputs, each element in the domain, gets transformed by the function and results in one specific output. That input-output pair becomes a single point on our graph. So, every point on the graph represents a mapping defined by the function. Scale of the axes must be chosen carefully to accurately represent the domain and codomain. This is a really common mistake students make, so pay close attention. If your domain or codomain includes numbers, you need to make sure your x and y axes are scaled appropriately. If you squeeze the scale too much or don't go high enough, you'll misrepresent the values and the shape of the graph will be distorted. Think of it like making a map. If you don't use the right scale, distances will be wrong. The type of graph, continuous or discrete, depends on the nature of the domain. Now, this is important for understanding what kind of picture you're going to get. If your domain is a set of continuous values, like all real numbers, you'll get a smooth, connected line or curve. But, as we saw in our second example, if your domain is a set of discrete values, like just a few specific letters or numbers, you'll get isolated points. You won't connect the dots, because the function isn't defined for values between those points. Let's wrap up our discussion on graphical representation of functions with these key takeaways. So, that's it for graphical representation. We've covered how to translate a function defined by sets into a visual graph and what to look for when interpreting that graph. This is a crucial skill as we move forward because graphical representation will be used extensively in more complex functions and concepts. Are there any questions before we move on?